In this lesson we will analyze the overfitting problem and cross-validation as a technique to address it. To introduce the overfitting problem, we first consider this made-up example. Assume that in the data at your disposal, all patients with high blood pressure are born in February and are left-handed. You might be tempted to choose the following decision rule, that is to classify at risk whoever is born in February and is left-handed. If we limit ourselves to the observed data, this decision rule is indeed able to perfectly identify all patients who are at risk. Nevertheless, such decision is clearly inadequate and most likely, it will perform poorly on a different set of data. This is an example of overfitting. Such solution is too specific for the observed data and it is not general enough. Let us frame the previous example in the machine learning world. Consider the linear regression shown in the figure. The R-squared associated with this fitting is 0.66. Which is far from 1. However, the residuals, the errors, are distributed according to a normal density, and we can therefore accept the regression. The same data can be also fitted with a polynomial regression of higher order. In this case, the R-squared is equal to 0.72, which is higher. We can ask ourselves if this model is better than the previous one because of the higher R-squared. The answer is no, because the data show a clear linear trend. The deviations of this curve from a linear trend can be associated with the measurement error of the individual points. And the polynomial curve follows also the errors of the data besides the trend. In this case, we are in the presence of overfitting. Not only the trend of the data is modeled but also the errors associated with them. But, when fitting the data we would like to avoid including this error. This discussion makes it clear that the R-squared alone cannot provide information on the goodness of fit. All data modeling techniques tend to overfit the data. For example, in the case of multiple regressions, each new variable added among the predictors increases the R-squared, that is, each added variable tends to explain better the variability of the output, but this variability may not be true, it could be only associated with measures errors. By looking only at the same data used for training the model, it is not possible to separate the error. Therefore, it is not possible to understand up to where we have an adequate fitting and from where we have overfitting. Possible solutions are the evaluation of the model by an expert, or the cross-validation we are going to present. When discussing the cross-validation, let's consider that the ML models are used to make predictions. Therefore, it is useful to evaluate their ability to make accurate predictions when they face new data different from those that have been used for their training. This process is called validation. Validation, by its nature, avoids overfitting because the result of the prediction will be evaluated on new data with errors that are independent of those of the training dataset. A possible way for validation is to wait for new data. The model is developed with the data that are available up to a certain moment. And then future data are weighted to evaluate the quality of the prediction against the measurement. However, waiting for new data is impractical because it requires a new study such as a new clinical trial, and to wait for the new data. A more practical alternative is to perform the so-called cross-validation. In cross-validation, the dataset is divided into two parts. A part called training set contains the data used to develop the model and train it. Another part, called test set, contains the data that will be used later to evaluate the goodness of the predictions. This is the simplest configuration. Sometimes the data are split into three parts, also including the so-called validation set. Then, in cross-validation, the model is developed with the training data and its behavior is then analyzed on the test data. If the results are satisfactory, the process is stopped. Otherwise, a new model structure is considered until the validation outcomes are acceptable. When the model is validated, it can be updated considering all data for training if necessary and can be finally applied. There are several techniques to divide the data between training and test set. The most common approach is to randomly divide dataset in order to eliminate any systematic difference. Moreover, if required, a stratification can be included in the random division to balance the characteristics between the training and the test set. Before going into some cross-validation techniques in detail, let's analyze how to evaluate the quality of predictions. We consider each point in the test set. The quality of the prediction for this point is measured by the prediction error, which is given by the difference between the observed value and the value predicted by the model. The goal is to minimize the errors over all points in the test set. To do this, metrics that summarize the errors over all data of the test set are used. The most common one is the so-called mean squared error, or MSE, which is defined as the average of the squared errors on the points. present in the test set. The squared value of the errors is included to ensure that all terms in the summation are positive, so as to avoid compensating positive error values with negative error values. This is similar to what we have already seen with the errors epsilon I of the linear regression. Let's now look at some specific cross-validation techniques. The first is called leave one out cross-validation. The idea of this approach is to consider only one observation in the test set, while all other observations stay in the training set. The error associated with the single point in the test set can then be calculated. This division and error computation is then repeated while varying from time to time the single observation in the test set, until every point stays once in the test set. Errors of all points when they have been in the test set are then combined, for example, calculating the MSE. We see an example in the picture for a linear regression where we have 9 observations. Each point remains only once in the test set, and the validation is repeated 9 times. The MSE of the leave one out cross-validation is then computed based on the 9 errors. The same approach is repeated on the same data, but considering a quadratic regression. Compared to the previous case, we obtain a lower MSE of the leave one out cross-validation. Therefore, the quadratic fitting is better. To show that the validation score is not directly connected to the R-squared, we consider, on the same data, a trivial fitting in which the function is a piecewise linear function that passes through all the points in the training set. In this way, the R-squared within the training set is exactly 1. The line passes through exactly all points of the training set at each iteration of the division between training and test set, but if we look at the MSE, this comes significantly higher and we discard this fitting. This simple example shows us that the cross-validation can avoid overfitting, while the R-squared is not able to raise alarms. The leave one out cross-validation has the advantage of doing model training with a number of data very close to those available overall. This is important because the quality of the fitting also depends on the number of training data. However, this approach is computationally expensive, because it requires repeating the fitting and the calculation of the error a number of times equal to the number of available data. In the case of big data, with lots of data available, this would mean repeating the process even millions of times. To solve these computational problems, the so-called k-fold validation can be performed. The idea is the same, but instead of leaving one observation at a time in the test set, one group of observations is dropped at a time. Operationally, the dataset is divided into k subgroups for each repetition of the cross-validation. A group goes into the test set, while the other k-1 groups go into the training set. As in the leave one out cross-validation, the error is calculated only once for each observation, when it lies in the test set. But the computational effort of this approach is much lower, since we only have to repeat the process k times. And k can be much lower than the total number of observations in the dataset. Also, in the training set, a relevant part of the overall data is present, which is required for a good fitting. The figure shows an example in the case of k equal to 5. The dataset is divided into 5 parts. Each group belongs only once to the test set, and the cross-validation is repeated only 5 times.